Hello students, in this lesson we will discuss the virtual work method, application of the virtual work method to calculate the slope and deflection in the beams and frames. This is also another form of the energy method. Last lesson we discussed about the strain energy and its different form is the Castigliano. Now coming to the virtual work, this virtual work is terminology is not new to you. Already you are familiar with this term in your previous subjects, like in particular like engineering mechanics courses. There, this principle of virtual work was used in the rigid body systems. What is that in rigid body system? The work done, virtual work done by the system of external forces during a virtual displacement is zero. But here in structural analysis problems, whenever you apply to the beam and frame problems, it is not a rigid body system, it is a deformable structure. So when we apply the virtual work to a deformable system, then the virtual work done by the external forces is equal to the virtual work done by the internal forces or stress resultants. So the external loads are like your point load, UDL or couple load, and the internal forces stress resultants are like your shear force, bending moment and axial force at any section of the beam. So this concept is used to calculate the deflection at any point or slope at any point in the beam and frame members. So without going much into the derivations and the theoretical part, we will move directly to the example system. How can we apply this virtual work method to get the slopes and deflections? So the another form of virtual work method is also a unit load method for calculation of displacements. The virtual work method is also alternatively called as a unit load method. Both are one and same. Based on the principle of virtual work, the unit load is derived. So after the going into detail of the derivations, you can go into the handouts to know more about the derivations. Now if we apply the example problem, first we will apply the example problem to a beam problem, then we will come to the truss problem. So in beam problem, that is in page 14, what is the handouts given to you, it is the unit load method is discussed directly. This expression is derived. What is that expression? Capital M small m dx upon EI integration. So integration over the length of the beam section. What is this capital M? This capital M is nothing but a bending moment at any section in the beam because of the external load. The external load may be a point load, maybe UDL, whatever the kind of load, you have to use that to get the capital M. Is like you have calculated like your Castigliano's theorem. Using Castigliano's theorem calculated na? Using the tabular form. So the similar approach also here. The capital M can be calculated like that only. Then what is the difference? The small m. Small m is that for a given beam problem or a frame problem, you remove all the external loads. You remove all the external loads other than end condition. You will intact the end condition as it is, but you will remove the loads only from the beams or frames. Then what next you have to do? Apply a unit load at the point where you want to have the slopes or deflections. If you want to have a deflection, either it may be horizontal deflection or vertical deflection. If you want to have vertical deflection, add a vertical load in vertical unit load there. If you want to have a horizontal deflection, put a vertical horizontal there. If you want a slope, then put a moment couple there at that point. Then by putting that unit load, whatever the moment you will calculate over the cross section, that is the small m. So we will understand this. How can you calculate the small m? By applying the unit loads in the following example problems. See, in this example, this is a cantilever beam having free end and UDL for some length of A and the span of the beam is L. We have to calculate the deflection and the rotation at the free end. So for the given loading system, we know how to calculate the capital M, the bending moment. So the bending moment is here calculated for the different sections, for the section AC and for the section BC. So if I take A as a origin, then for the section AC, this is the bending moment expression. If I take again as a origin for the section CB, the range is A to L. If my origin is A, then for the CB segment, the C starts at a distance A and B ends at a distance L. That's why it is A to L. But the same thing, if I take C as a origin, then my range will change. But in this particular example, the origin is considered as A. So that's why for the section AC, this is the bending moment, and for the section BC, this is the bending moment. And we know the origins. That is the range is given here. That's for the bending moment for the heavy external load. Now, as we said, to get the vertical deflection at the free end, here the external load is removed and end condition fixed end is kept intact. We applied a vertical unit load here. So applying the vertical unit load, again we calculated, because if I apply unit load here, whatever the section point I take, the bending moment is not going to change. So rather giving the two sections, I can take only in one section I can calculate the bending moment. And the same thing, the origin is this point only. By considering this point as origin, and we can calculate the bending moment at any point x. That is, if for example, if I take this is the point where I would like to have the bending moment at any distance x, and x is, that is origin is A, so this distance is x. Now what is the bending moment here? So let me show you how I am getting. See here, if I take this is the section, and from here to here, if I consider this is the x, if this is the distance x, then the bending moment at the distance x is equal to nothing but equal to 1 into this distance. So this distance is nothing but, this is L, and here to here is x, so 1 into L minus x. And here the bending moment is hugging moment. We are calculating bending from the right side clockwise, the minus sign, that's minus 1 into L minus x. So that way we can calculate the bending moment, small m. Okay, that's for the unit load. Now to get the vertical deflection here, we can do the integration. That is capital M small m dx upon EI. Okay, and this capital M having the two segments for this range and for this range, but this range is 0, so it is no effect in the integration process, only this. So this part multiply by this part doing the integration over this 0 to A, because from A to L this portion is 0, so it is not being taken any effect. If it would have been some value, then we would have add this value here. So with this we can calculate the vertical deflection at the free end. Okay. After getting the vertical deflection, now the same way, if I want to calculate slope at the free end, so the external load what we have calculated, the external load what we have calculated, that is not going to change, that will remain as it is. Okay, and only the small m we have to calculate. Thus now here the small m is for the slope, we have to apply a unit couple here. And after applying the unit couple, and again similarly at any distance x, what is that moment? Because there is no distance to be multiplied, because it's itself a moment, that's itself a 1 only. So that 1 is equal to minus 1, and by putting m into m minus 1, this is small m is equal to minus 1. And theta b, that is slope at b, is equal to multiplication of this capital M is this, and small m we calculated for the slope, that is minus 1, and capital M small m by multiplying we are deriving this expression. Finally we calculate this value. Okay, this is what you have to use to calculate the unit load method or virtual load method in the beam problem. Alternative approach is also there, but that is not of that versatile, so I will not suggest to go into detail of that. Only you understand this part. Now another example is there here also. This is like your Castigliano's problem. This problem also can be expressed in form of the tabular form, like here. See, in this problem, this is the overhanging beam. We have to get the free end, the deflection of point C. So this segment is divided in two categories for the range AB and BC. So this table is here AB and BC. Similarly, to get the bending moment for the AB section, A is considered as the origin, so that is this distance is x. Similarly, to consider the segment BC, C is considered as the origin. So whenever you will calculate the bending moment, you will consider the calculate bending from this origin.